Hello, it's Keith here, and this is lesson 22 of the ChibiAkumas series of my Z80 programming tutorials. Now, last time we had a look at how to create an RLE with the Aku sprite editor and how to view it on various systems that were supported. Today we're going to look at the Amstrad CPC version of that decompressor. The CPC version was the basis for the others. I'm probably going to go over the MSX version in some detail, but the Spectrum version is virtually identical, so if you're interested in the Spectrum version, the source code's available. It's just not as well code commented as the version we'll look at today, but as I say, in most cases it's actually the same. Now, if you don't know what the RLE is, please take a look at the last lesson. It's basically a compressed file. We're going to look at how that compression works today, and we're going to see how the Z80 decompressor actually compresses the data. So when we view an RLE, we are passing some data to the RLE decoder. There's the start of the data, there's the end of the data, there's the Y line, that's the vertical start position, there's the width of the data in bytes, and there's the right hand side because the drawing goes right to left. So we specify the right hand side to position the bitmap on our screen in the x-axis. Now these are passed to the RLE decoder, and here it is. Now the first thing we do is some initialization. That's pretty much this section here. So as with most of my code, I'm using self-modifying code here, and we are modifying in the width and a few of the other parameters, the end parameter here, using self-modifying code in various positions. Next, what we're doing is we're calculating the starting screen position of the line we're going to draw to. So effectively what we're doing is we're loading in the B, which is the Y line, into the accumulator here, and we are repeatedly using this, and we are calling this get next screen line, HL here, which is moving the memory cursor down a line. Now we define the screen position in HL here using C0, which is the start of the CPC screen, C000, and the horizontal offset in IXL here. And then we're using this, but this function is actually designed for resetting the screen position after a line's been drawn. And so this is automatically adding the width of the bitmap, because we are drawing right to left. So we're actually having to subtract the width of the bitmap to correct it here, because as I say, this is basically being repurposed here. It's probably not that efficient, but we only need to do this once at the start of drawing, so it's kind of an inefficiency we're overlooking here. So we're repurposing that function. Now when we get down to here, we're ready to actually start drawing. We're setting E to 255 here. The E register is used as a marker. On the Amstrad CPC, there are 2 nibbles per screen byte, and we are doing those separately, and there are 2 functions to handle each half because we have to do bit shifting. And so if E is 0, we're doing one half, and if E is not 0, we're doing the other half. So we're starting with E as not 0 here. That's what we're doing. Now we're ready to actually start processing bitmap data. So we increase HL here, we read in a byte from HL, which is our source data, and then we are seeing what data is here. Now let's just remind ourselves of what kind of data there is. Well, the first one is RLE data. That's where we've got a nibble and a repeat count. The second one is linear bitmap data. This is where there is a set of uncompressible data, so we're just collecting a set of bytes and showing them straight to the screen. And then the third one is repeating byte data. This is where there's a repeated number of the same byte, but that byte apparently can't be RLE compressed. So we've got these 3 options here, and we're going to have to look at how to filter these out depending on the bits. So what we're doing here is we're taking the RLE count here, that's the bottom nibble of the byte we read in. If that bottom nibble is 0, then we don't have RLE data, so we're jumping away. If we do have RLE data, we are having to shift that data around. Now it's important to understand on the CPC that the visible screen, 2 neighbouring pixels, with each pixel taking 2 bits on screen mode 1, those pixels don't actually appear next to each other within a nibble. They're actually 2 bits apart. And so we're having to shift the bits around because we're basically storing the data in a visual representation for compression efficiency. We're having to convert that into a logical representation for what the screen memory actually stores. So we're separating the 2 bits in the nibble and moving them into the correct position for the byte data of the screen. So at this point now, we've got our C register here storing a repetition of the bits within the nibble, and we can use this later on when we're actually drawing our screen data. Once we've prepared that nibble, we're then checking our count. Now if the count is 15, i.e. all the bits are 1, then we're loading in a following byte and adding that to it. If that byte is 255, we're loading another one and another one. This allows us to have the compression efficiency of just using 1 nibble as a count for small runs, but for very long runs we don't have to have any more header bytes to define those runs. So we're getting a win in both ways there. So this is adding those extra bytes to our count here until we get one that isn't 255. At this point, we're checking E. Because we could already be halfway through a screen byte, we're needing to check if we're halfway through or not. And if we are, we're branching out here to flip our bits around. Now at this point, we have a speed up. We have a command that will do entire bytes of data much more quickly. We're checking if it's worth branching out to that. And if it is, we're branching away here. So if there's more than 4 nibbles left to do, we're branching out. Otherwise, we're carrying on here. Here we're getting our screen position we're drawing to via self-modifying code. This SM ** here is my marker for self-modifying code. So at this point, we're now taking the bits of the pixel position of the screen. We're then ORing in the last one. So here we are taking our mask of the nibble we're drawing to the screen. We're keeping the bits, ORing in the last definition here, and then saving it back here. And then we're doing the same here for the other bits. That's the second pair of pixels of the screen. And then we're saving it back to the screen here. Each time we're decreasing IX, which is our counter, and we're decreasing HL, because remember we're moving right to left. At this point we're checking B, and we're seeing if we've drawn all of the bytes of this line of the screen. If we have, we're jumping over to next screen line, HL, which will increment the screen memory address that we're writing to. Now at this point we're needing to check if we've completed all of the run of this RLE. If we haven't, then we're jumping back up here. But if we have, then we get to here and we store our byte number here, and then we store the screen address we're currently writing to just here. Now of course at this point we now need to check if we have any data left to work with. If we're at the end of our RLE data, then we are going to return, but if we're not, then we're going to jump all the way back to the top and we're going to read in another byte and process that accordingly. So that's the entirety of the RLE decompression code, and it's important to point out that if we disabled all the other modules within our RLE compressor, that is all we need to decompress, but it would be much slower and it would also be less efficient. So I did add these other functions for a bit of efficiency. Now here we've got the code that handles the flipping of the bits around depending on what part of the screen we're working with. And that's where we've drawn half of a byte with our last RLE header, and the new RLE header is going to continue on halfway through that byte. So these are flipping things around for that. Here we've got 2 get next screen lines. One works on HL and the other works on DE here. And the reason for that is that some parts of our code use DE and other parts of our code use HL. So we've got 2 versions there. And of course these are optimized for the CPC screen. Now the RLE decompressor on the CPC always decompresses to the standard screen memory address. You could reprogram it to load to the alternate one, but it's so slow that really you wouldn't want to use this when you were page flipping, because it wouldn't really make any sense. So in the cases that I didn't want the user to see the RLE bitmap being drawn, I just blacked the screen out. Now we've done the first of our data types. Now we're on to plain data. Now this is where we have a sequence of bytes that are all loaded from the RLE data stream straight to the screen. So again, as before, we're currently checking if the counter is at 15. If it is, we're loading in more bytes until we get one that isn't 255. That gives us our total count here. And then what we're doing is we're just loading in bytes from HL, saving them to DE, decreasing DE being our screen memory location, decreasing DE each time, decreasing our counter here, and we're repeating until we either get to the end of a screen line or until we've run out of data. And then once again we jump back to check for the header of the next section. The third data type is 1 byte data. If you remember, this is where we have a single byte repeated many times. Now as before, we're loading in a byte here. We're seeing if it's 255. Once we get to a byte that isn't 255, we've got our count, and then we're going to actually read the data. Next we load in our single byte here and we save it using self-modifying code here, and then we are just going to be repeatedly writing that here in this loop until we filled all of the memory here. Now the final one is the Byte Nibbles. Now this is where we've got RLE byte data, but we have more than 4 RLE nibbles left to draw. So rather than working at the nibble level, we're going to work at the byte level and just fill those much more quickly. And so that's what we're doing here. Essentially, it's in principle the same as the code before, but now we don't need to do any masking. We're just copying C straight to HL. We're decreasing HL. We're decreasing DE twice because remember this will be expecting to work in nibbles, but now it's working in bytes. And again, we're just checking if we've got to the end of a screen line, and we're just repeating as required. And that's really all there is to it. So the RLE code really, I mean, there's quite a lot of it, but the concept's very simple. If you want to, of course, you could make various optimizations to it. And as I've said before, I'm not trying to pretend this is the best RLE compressor decompressor. I'm quite certain it isn't the best. It's just what I was able to come up with. And as I've said many times before, I really struggled to get this thing working. It took me a weekend to get it working at all. I was tearing hair out, screaming at it. You know, it was real struggle for me to get this going. If you persevere with these things, if you just think them through and just keep things as simple as you can cope with, I think you can probably create stuff that is really beyond what you thought you could, because I really was skeptical I could pull this off. And the real struggle with it was I was writing the compressor on one side and the decompressor on the other side, and if either had a bug in it or both had bugs in it, neither would work at all, and it was just showing garbage to the screen. Once I had the first compressor working, porting it to the SAM coupe actually only took an evening. So although there are still efficiencies that I'm sure could be made in this code, I'm much more happy to have working code that I understand than the best code in the world ever. Anyway, I hope you've enjoyed this. Maybe you found something useful in it. Thanks for watching today, and goodbye.